So, good evening. Anish, can you hear me?
Yes, sir, you're audible.
Hello, can you hear me?
Yes, sir.
Can you hear me, Anish?
Yes, sir. I can hear you.
Um, can you talk now, Anish?
Hi, sir. Hello.
Can you hear me, Anish?
Yes, sir.
Can you speak now?
Yes, sir, you're audible.
Okay. Anish, can you speak once? Yes.
Yes, sir, you're audible,
Okay.
sir.
Okay. 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 Sorry. I was not able to connect. We are fine. Thank you, Anish. Okay, so we are in the week 4 of this course on finite element method and computational structural dynamics, and we are uh, we were going through introduction to finite element and also uh, one-dimensional problems, solving one-dimensional problems using finite element method. Uh, so we saw in the last week we started the bar problem. Now uh, we will go through another problem which is in one-dimensional. That is a beam problem. So like why do we had to how did this uh, concept of finite element method came in? Because like uh, whatever the problems in general, like in structures or like in any structure in real life, we can see they have like irregular domains. Like you can have some machine like this, uh, which has this shape, and or let's say you can have some shape like this, or there can also be some uh, structures which have some irregular domain like this, like some natural structure is there and you want to analyze its properties. It can have some kind of domain like this, like whatever the problem which we saw, like using weighted residual method, or using the variational approach, or using the Galerkin approach, whatever we saw, like we had this kind of integral, right? So we had to take the weighted average or weighted residual of the weighted residual, and we should make this somehow equal to zero. And for that, you can see that we had to integrate over this domain. So domain is nothing but this is the domain of the structure, right? Like this, whatever the uh, in whatever uh, region we want to evaluate the structure, that is nothing but the domain. So this is the domain. This is the domain. This is the domain. So for a simple brawl problem, like a line is the domain. So this line is the domain. For a beam also, this is the domain. But as we go and solve more complex problems like in 2D or 3D, we will have some irregular domains like this. So doing like for a bar, like if I want to like do integration over this domain, I'll just do integral 0 to L. And if I have some area like a square, like two-dimensional structure, like this, I can just take like this, right? Like I can just take integral over area, uh, that I can replace this with a double integral. You can say this is from 0 to a, and this is from 0 to b, like 0 to a and 0 to b, and I can do this integration because these are like regular domains. It is easy to do integration and all these kind of things. But if we take this complex domain, like if a structure has a complex domain like this, then it will become difficult to do this integration. Like you cannot physically, it is not physically possible to define integration and also interpolation about these domains. So somehow, but we want to solve this problem, and we want to estimate and analyze this kind of irregular structures too. So in order to do that, like people came up with this uh, concept of finite element. So in that, what we do is like we take any kind of irregular structure like this, and we divide this into the domains, like small domains, for which we already know what, like we can do this interpolation and integration very easily. So if I have a structure like this, I'll divide this into like uh, squares like this, and each of this square I'll call this as a, you can call this as some uh, you can call this as a element. So now the problem can be solved very easily. So this each uh, each box is called as an element. So so the whole domain is omega, but I can take this whole domain as a union of all these elements. And we have to see that one element cannot overlap uh, about another element. So it has to be continuous. Like one element should be beside two elements can be beside each other. Like they share a boundary, but they cannot have overlapping. So there are a lot of conditions which we have to satisfy. So so what we do is like we take this domain, we try to do the weighted residual over this domain, and like that we will take weighted residual over all these elements, and then we try to combine them, and then we will solve the problem and get the displacement field of this structure. So that is the methodology of finite element method. So we have something like this. We have something like this, integral w into a residual, some kind of residual, is equal to, now I can make it like this. So if I have n elements, I can divide it into n integrals, and I can combine all of. So this will be residual over this element. So this is equal. So we have gone, we have seen the bar problem also, that during this, and we have moved on in this week to solve the beam problem. So one analogy you can think of it is like as this Lego model. So you can have this like a building blocks. So these are the building blocks. We take all these building blocks and we make this Lego model or this structure. So each element you can call this as the uh, each element you can call this as a each block you can call this as an element of this. Okay, and this you can see that two blocks share the boundary, and if you move the structure, the boundary between these two blocks will have the same displacement. So that condition of compatibility should be satisfied. So there are conditions: compatibility, consistency, all this, which was as it was taught in the class. So it is like we are dividing and then conquering. The You can say that kind of philosophy we are using in finite element method. So now we will go directly to this problem. So this is a very extensive problem, and if we solve this, like we can understand uh, for a beam how we can derive the governing differential equation, and then identify the boundary conditions, whatever the structure it is there, and from that we will develop the weak formulation, and from the weak formulation we will develop the element stiffness matrix, and after developing that we will try to get what is the deflection at the free end of this cantilever field, and there are some properties given according to that. Using those, we will find out our numerical result. So first thing I want to do is take this beam system and I want to uh, derive a governing differential equation or the equation of motion uh, of the beam. So we will use the variational method. So one way of doing this is also using the we have already seen that. So we can also use our uh, Newton's second law. Newton's second law can also be used to get the governing differential equation or the conservation of momentum equation. But here we will use variational principle or the energy principle to determine the equation of motion. So that is a very easier and also it is a very useful way. If we go and want to derive the governing differential equation for more and more complex structures, like beam is a very simple one. You can apply Newton's second law easily. But if you want to go and do it for more complex structure, you cannot easily apply the Newton's second law. So using energy approach will always be helpful compared to that. So so here there are few conditions. Like we will take the Euler-Bernoulli beam theory. So assumptions. These are my assumptions. So Euler-Bernoulli beam theory. In Euler-Bernoulli beam theory, plane section remains plane and it is perpendicular to the uh, uh, axis of the beam. So Euler-Bernoulli beam theory will be used, and we will assume that the deformations are elastic in nature. So that means like if I remove the load, the structure will come back linear and linear elastic. So I I will also assume that my displacements are very small. So these are few conditions. Like Euler-Bernoulli beam theory also uh, uh, gives the condition that shear deformations are neglected. So that's why this uh, lane section will be perpendicular to the longitudinal axis of the beam. Sections will always be perpendicular. So that is the condition of Euler-Bernoulli beam theory. So anywhere the section will be perpendicular to this axis, neutral axis. If this is not perpendicular, that means shear deformations are happening. Then we cannot use this uh, Euler-Bernoulli beam theory. We have to go and use some other beam theory like Timoshenko beam theory, or there are more higher order beam theories. If you like, if you have gone through some course like theory of elasticity or continuum mechanics, you might have seen these more complex theories. So Euler-Bernoulli beam theory is like usually taken when this thickness of beam is very less. So if your beam looks like this, then you can probably take Euler-Bernoulli beam theory. But if your beam has a high thickness, something like this, let's say this is fixed. If I have a beam like this with very high thickness, then you cannot neglect shear deformations. So that time we have to go through Timoshenko beam theory or some other beam theory. But for time being, uh, we will here we will only go through the Euler-Bernoulli beam theory. So in variational formulation, first thing we have to define is the potential energy and then we try to minimize it in variational sense. Okay. So this is the beam which we have, and I want to define the potential energy. So potential energy will be equal to strain energy minus the work done. Okay. So this is my potential energy. So strain energy can be defined as this, right? Like half into sigma xx into epsilon xx dV. Because the beam fibers, uh, whatever the beam, like if you try to bend a beam, the fibers will elongate or they will get compressed. Like if a beam is bending like this, the top fiber about this top fibers will get compressed. So they will have some kind of uh, axial compression, and the bottom fibers will get elongated. So these will be experiencing this kind of stress due to the bending. So stress and strain. So like you know that strain energy, like if you have a uh, you have some kind of structure like this, like a strain displacement relation, uh, like this, area under this will give the strain per unit volume. And if I want and if I want the strain energy to over the whole volume, I will take the integral of it. So that is the simple thing. That's how this formula comes in. So strain displacement relation, strain and stress and strain relation. Because as I've said, this is a the structure which we are looking at is a linear elastic structure. That's why this is a triangle. So that's why strain is directly proportional to stress is directly proportional to strain. So that you might have also heard in the Hooke's law, which is for linear elastic materials. So that's why we are taking here this area under this curve. We are taking it as half into sigma xx into epsilon xx. Okay, and I want this energy over the whole volume. So that's why I'm integrating over the volume. And the work done. So work done is nothing but the force into displacement. So this force, like I can write this force as Q into 1 minus x by L. Like if I want to find out, I want to find out this maximum intensity of this force is Q, and the minimum intensity is 0. This is a uniformly varying load. So if my if x is equals to 0, if I'm starting x from here, if x is equals to 0, at this point the intensity is q, and if I am going to the end of this wheel, at the free end, the intensity is L. So I can write this load intensity as q into 1 minus x by L. So now I want to get the work done. So if at one point, let's say at any point on the beam, the work done will be q into 1 minus x by L. That will be the load at that point into the displacement experienced by the beam in transverse direction. I will take it as V here. But I want the work done by the load over the whole beam, right? So that's why I will take this integration over the whole length of the beam. So this will be the total work done by this load. Yeah. Now I can, because the beam has a constant cross section, which means this cross section of the beam is constant throughout the length. Okay, this shaded part is constant, right? Uh, if this is not constant, the beam will something looks like this. Here, the cross section is not constant; it is varying, linearly varying, or something. But here we are assuming that this cross section remains constant throughout the length. So that's why I can make this integral and convert this from volume integral to one area integral, and I can write this as so by Hooke's law we also know that sigma xx is equals to E into epsilon xx. This is Hooke's law. Now I can replace epsilon xx with this here, and I can write epsilon xx is equals to sigma xx by E. So that's why here it will come sigma xx square and dA into I am making this volume integral into a area integral, area into length. So that's what I am doing here, and this will remain same. So because area is constant, as I have said, I can write this as integral 1 by 2 E into sigma square uh, A into dx, like this. And this will remain the same, 1 minus x by L V dx. Now, we know this uh, Euler-Bernoulli beam equation, the relation between stress and the moments, the famous uh, equation which you might have heard in the strength of materials class while you were learning the Euler-Bernoulli beam equation, which is m by I is equals to sigma xx by y. So moment uh, by this is equals to sigma xx by y. Now I can replace here with the same thing. I can replace sigma xx is equals to m y by I. So now this will become 1 by 2 e into uh, m by I whole square into a into uh, y square. So instead of writing this, I will still write this as dA. I will not make it. I'll still take this area integral. Now I can take out this area integral separately like this, and I have done the replacement, and this will remain same. Now this is nothing but the moment of inertia of the cross section. So that I can write it as I. So I can replace this with I. And we also know this relation, right? So m by I is equals to sigma xx by I. Sigma xx by y is equals to e by r. So now I can replace m with like I will take this m by ei is equals to e by r relation and substitute m with ei by r. So r is nothing but we can write this as dou square y by dou x square. So 1 by r is equal to dou square y by dou x square. So dou square y by dou x square is called as the curvature of the wheel. So now if I substitute m is equals to ei dou square y by dou x square by I whole square and this dA into y square over the area integral will give me I, and this is dx, and now I can take this. Okay. Now if you square this and do the simplifications, we will get integral 0 to L 1 by 2 ei, and sorry, this y is nothing but this is not y, this is v actually. Y and v are different. Here also it is v. So I'm taking vertical deflection as v, not y. So y is the variation uh, height of the height of the fiber from the neutral axis of the beam. That is different. So now this will be my final result, which I will get after this simplification. So we have got the uh, uh, potential energy in terms of the primary variable. So primary variable is nothing but V here. So V is the primary variable. So we have got this U in terms of V. So that was our first goal. We have achieved it. Now we have to move forward and consider the variation of U and set it to 0. So that is nothing but you are minimizing the uh, uh, potential energy. So we will consider the first variation of U and set it to 0. So we want delta U is equals to 0. So delta U is nothing but U, we will write U that will be 0 to L 1 by 2 EI d square V by dx square whole square dx minus integral 0 to L Q into minus 1 minus x by L V dx equal to 0. So now I will apply this variation over this uh, whole U. So now I will get this because U is the primary variable. So we want to apply variation with respect to that. So that will give me 2 into dou square V by dou x square and into dou square delta V by dou x square. This is similar to differentiation, we can say. So you have to take uh, take this and do the differentiation once, and inside term also should be differentiated. So we are applying the variation and like which is similar to differentiation in some kind of thing. And now we also have to apply here. So because v is like a single term here, I can directly apply over the variation, and this should be equal to 0. So now we have this equation, and like I want to uh, like there are this two can be cancelled here. Now I have this equation which is equal to 0. Delta u is equal to 0. Now I can what I can do is like I want to convert this into a weak form. So uh, for that I have to do uh, integration by parts. So integration by parts, the first step we will do. So we will take this ei d square v by dx square, and we will I hope you know what is integration by parts. Something you have, if you have something like this, you can integral uv, you can write it as u integral v minus uh, u dash integral v. So this is integration by parts. So first I will take u into integral v. So here u is pi into d square v by dx square, and integral over this will be v is nothing but d square delta v by dx square dx. So I want to integrate this, and we will get d delta v by dx, and we have to integrate it from 0 to L. So the integration limits are 0 to L. So, and next we have this u dash into integral v. So u dash is nothing but vi into I can write dy dx of vi into d square v by dx square. This is u dash, and integral v is d delta v by dx. And this is the integral over 0 to L. So we have done the integration by parts once. And there is also this term, which is 0 to L, u into minus 1 by x delta v to dx. So now you can see I have this integral again. I can do integration by parts once more, and I can get this integration like the finally I can integrate this to get this term only with respect to delta v. So that will be my target. So this I'll keep it like this. These two terms I'll keep as it is, which are uh, vi into dou square v by dou x square d delta v dx integral 0 to L, and this term integral 0 to L u into 1 minus x by L delta v dx, and I have this term which I will do integration by parts again. So you can write apply integration by parts. So now this is my u and this is my v. Sorry, this is my u and this is my v. Okay. So that will be so I can take this in a bracket or like I'll do it like this. So that will be minus dy dx vi into d square vy dx square is equal to into delta v 0 to L and plus now I have to do integral v dash integral u dash into integral v. So u dash will be nothing but integral 0 to L d square by dx square. This is u dash and our integral v will be delta v will be equal to and this will be equal to 0. So now you can see the finally we have got this form and now we can uh, get the governing differential equation from this. So what we will do is like we will take all the terms which are integration terms which are with respect to delta v. So I can take this integral evaluation term separately, which is d delta v by dx integral uh, 0 to L and this term also I will take which is d by dx into ei dou square v by dou x square delta v 0 to L. I will take plus integration terms whatever are there I will take integral 0 to L d square x by dx square d square by dx square ei is d square v by dx square and minus this q into 1 minus x by L is also there which also has the same integration and this can be multiplied with delta into dx is equal to 0. Now I will apply this integration limits. So this and this I will apply at x is equals to L and apply at x is equals to 1 and we will see what we can do about it. So ei into d square v by dx square d delta uh, v by dx at x is equals to L minus ei into d square v by dx square uh, into d delta v dx at x is equals to 0. And now the second term, which is minus d by dx vi v square v by dx square delta v at x is equals to L plus d by dx of ei into d square v by dx square delta v x is equals to 0. And we have this term. I will write this as, let's say, I'll just write this as um, a g, okay? I'll take this as g for simplicity to write. I will take this as 0 to L g delta v dx is to 0. So for this entire thing to become 0, each individual term should become 0 because delta v can be arbitrary, right? Like it can change. Like we can take any delta v, but this entire thing should become 0. So for we can write this for the variation to vanish, to vanish, each individual term should vanish because delta v can be arbitrary. It is not a fixed value. Hence, uh, governing equation can be given as governing equation and boundary conditions can be obtained for after doing that. So if I want this only this to be 0, if I want like as I said, like each individual term should vanish, so then this should become 0. So this is one term, and this should become 0. For this to become 0, if like delta v is like varying arbitrarily, the only way this can become 0, this integral will become 0 is g is equals to 0. When g is equals to 0, this integral will become 0 in the case of delta v being arbitrary. So now g is nothing but we wrote g is nothing but d square by dx square ei into d square v by dx square minus q into 1 minus x by l equal to 0. So this is my governing equation. This is my governing equation of the wheel. And this is in the domain omega, which is x omega such that x belongs to 0 to L. So my domain is over the whole length of the wheel. Okay. And now it's equals to 0. The boundary conditions also have to be defined. So if these variations are arbitrary, so these terms should become 0, right? So at x equals to 0, at x equals to 0, uh, let's say you are, what is this? And let's say you know dv by dx, the slope dv by dx to be specified I will explain this dv by dx to be specified, or vi into d square v by dx square is equals to 0. At x is equals to L, dv by dx, sorry, another condition will be there here at x equals to 0. V to be specified, or E into d by dx of Vi into d square v by dx square is equals to 0. Okay. At x is equals to L, dy by dx need to be specified. Same conditions. I will write okay, at x is equals to 0 and at x is equals to L. Okay. So what does this mean? I'll explain. So if you have a cantilever beam like this, you have a cantilever beam like this. So there are two boundary conditions. Like here we can define four boundary conditions. Okay, for this cantilever beam, we know that this end is fixed. So here V is equals to 0. So the transfer displacement of this beam is 0 here. So V is specified. Okay, and dv by dx is also 0 here because the slope is also 0 here. So this beam is fixed at this end. So that's why V is equals to 0 and dv by dx is also equals to 0. So both the things are specified. Okay. But when I come to the free end, I cannot specify the boundary condition. So that's why, like, I don't know what amount of deflection this beam will go through due to the applied load. And I don't know what will be the slope of this beam due to the applied load that we have to determine. But I know that if there is no load acting on this free end, let's say load is acting at some other point, then this uh, bending moment at this point on the cantilever beam will be equal to 0. So bending moment is equals to 0. That is nothing but EI into d square by dx is equals to 0. So this is nothing but the bending moment. And also shear force is also at 0 at the free end. So that is nothing but di by d by dx of ei into d square v by dx square is equals to 0. So at each boundary we have to specify uh, either this uh, either this uh, slope and displacement we have to specify, or we have to specify either uh, this uh, bending moment and also the shear force. Something from this each we have to specify. So at the boundary conditions, so at the boundaries of the beam. So here at the free end we are taking these two boundary conditions. Okay, at the free end we are taking these two boundary conditions because we know here at the free end. But bending moment is not 0 at the fixed end, and shear force is also not 0 at the fixed end. Okay, so that's why we are taking these two. We know here at the fixed end. At the free end, we don't know this. So that's why we can take this. We know that shear force and the bending moment will be 0 at the free end. So that's why we will take this boundary condition at this boundary. So suppose if you have some, let's say instead of this, we have some simply supported beam. So if we have a simply supported beam, something like this, so it will bend like this. In the simply supported beam, we can take at this point v is equals to 0, and also at this point v is equals to 0. So now I have taken this v. So now I cannot specify, like I cannot specify I cannot say that shear force is equals to 0 here. So v is specified. So now another boundary condition I have to give, which is with respect to slope or bending moment. So because here slope is not is equals to like slope is not equal to 0, uh, this bending moment will uh, be equal to 0. So slope will be having some value at the boundaries of the simply supported beam. Bending moment will be 0. So these two will be the boundary conditions at each boundary in the simply supported beam. So this is how we can determine based on the structure which we have. We can get the boundary conditions accordingly. Okay. So either it has to be V or shear force, or either it has to be slope or the bending moment. So at each boundary, we should have two boundary conditions that we have to determine depending upon the structure which we have. Okay. So for our structure, this is the cantilever beam. So here V and slope will be 0 at x equals to 0, and bending moment and shear force will be 0 at the free end. So that's what we'll get. So for the given structure, I will take uh, for the given structure, this is our uh, governing differential equation, which is d square by dx square into vi into uh, t square v by dx square minus u into 1 minus x by l equal to 0. And this is over the domain which belongs to x 0 to l. And the boundary conditions, sorry, this is not here. And we have the boundary conditions at x is equals to 0, v is equals to 0, and dv by dx is equals to 0. Okay. And second boundary conditions we have uh, at uh, at x is equals to L of the cantilever beam, we have the bending moment is equals to 0, and the shear force at the free end of the beam is equals to 0. So these two boundary conditions with respect to the if I have boundary condition with respect to the displacement and the rotation in beams, though these two boundary conditions will be essential boundary conditions, because these are here we will have two primary variables. In bar problem, only u was the primary variable. In a beam problem, we will have two primary variables, which is v and dy by dx. So both are the primary variables which we have. So this is also an essential boundary condition. So we have two essential boundary conditions at the fixed end. And these are the natural boundary conditions. These are the natural boundaries. So this is how we will get the governing equation of the structure, governing equation of the beam, by using the variational principles or the energy principle. We have finally got the governing equation, and now we will go and get the weak form using our weighted residual approach, and uh, we will use we will do the finite element analysis. So the next step after getting the governing differential equation and the required boundary conditions of the structure, so mathematical modeling is done. Now we have to analyze the structure. So mathematical model is there, and now we have to solve this mathematical model to get the uh, displacement field or the required results which you want to analyze. So next step is getting the weak form. So in order to get the weak form, let's say you assume some solution for V. So let's say we we will assume like whatever we do in approximate method, we will assume some solution and we try to get the residual. So because V is not equal exactly equal to the exact solution, we are assuming something. So there will be a residual. So that residual over the domain will be d square by dx square into ei into d square v by dx square minus q into 1 minus x by l. So this is my residual because v is not sorry, this is v cap. Okay. So because v is whatever the solution which we are assuming is approximate, this is not becoming zero. So there will be some residual which is left and we have to somehow minimize it so that we go near to the exact solution. That is our goal. So now we will go to the we will go and write the strong form uh, method of weighted residual, which we will get integral w into, and I'll take this, or you first I will write this as r omega is equals to zero. This is our weighted residual approach. I want to make the residual uh, zero in an average sense. So now I have r omega is equals to this d square by dx square ei into d square v cap dx square minus u into 1 minus x by l dx is equals to 0. Yes. Okay. Now I will take and apply this multiplication with the wave function for the each term which we have. Take this. Take this. And I'll take each term separately. Have d square by dx square ei into d square v cap by dx square. And there can be two terms which can be derived from this. This, this 2x by l equal to 0. Now you can see like whatever we have done this. Now we have this term, this term. We can you can we can see that like we can integrate this by parts, and let's see what we get. So doing integration by parts. So I will have this is my u here and this is my v. Here additionally there is this. So I will get w into d by dx uh, of ei into d square v cap by dx square and 0 to l. and I have uh, integral 0 to L u dash, which is nothing but dw by dx, integral v, which is dy dx, ei into d square v cap by dx square dx. And let's say I will take this, uh, I will take this entire thing as uh, something like L. I'll take this as uh, LW. Okay. So I'll take this as LW. Finally, I will write that. Yeah. So this is not, this is, uh, I can take, yeah, write this as LW. Now, I have this term again. I have this term again. I can again do integration by parts and I'll get something. So this term is there, which will be as it is. And this term, I will get integration by parts. After doing integration by parts, I'll get this 0 to L plus integrate 0 to L d square W by dx square into EI into d square V cap by dx square dx minus LW, whatever it is there. So now I have this entire equation, which is equals to 0. Now you can see here, uh, after after taking this strong form, so this is the strong form, okay? This is the strong form. And doing integration by parts two times. Now you can see here in this strong form, there like we had to differentiate v four times, like d square v by dx square uh, was two times. Again, like there was one integration outside, which will differentiate v again two times. Now, finally, after doing integration by parts two times, you can see that the equation which we are getting at the end, you can see all the terms have only differentiating v only twice. So the requirement on the differentiation of V is reduced. So that's why we call this as a weak form. So if we had taken a strong form directly without taking the integration by parts, we had to assume a solution which will which should satisfy this derivative condition. So you had to take a function such that it should be differentiable four times. But now you can choose VCAP such that it will be differentiable two times. So the condition has been relaxed. So now you can also take this, like I'll take this to the uh, whatever we have, this separately on this side, which will be equal to integral 0 to L d square W by dx square EI into d square E cap by dx square dx is equals to, I'm sending these terms to the right hand side. I have W into dx d by dx d square V cap by dx square is equals to at x is equals to L, right? So at x is equals to L, at x equals to L. Okay. Plus same thing at x is equals to 0. And this now I will do for this. So it will be plus d by dx, dw by dx, ei into d square v cap by dx square at x is equals to L minus uh, d by dx, dw by dx, ei into d square v cap by dx square at x is equals to 0. And I had this LW, which I will write. So this is a very big equation, which is it w into q into dx plus integral 0 into w qx by L dx is equals to 0. So this entire thing is equal to 0. So now I know that like there are boundary conditions which we say at x is equals to L. We know that at x is equals to L, we knew that because of the structure at x is equals to L, we know that the bending moment is equals to 0. So that is one boundary condition. And at x is equals to 0, we know that our uh, uh, slope should be equal to 0. Okay. So we will see how, but this will become 0 because this has to be satisfied. Boundary condition has to be satisfied. So this will be equal to 0. And at x is equal to L, uh, uh, this is shear force, sorry, this is shear force and this is bending moment. Both has to become 0. Okay. So these were our boundary conditions. We have got this. This is the weak form. So now we will assume a solution which is differentiable twice. Okay. So let's. So in this case, in the beam equation, we had to like if we take a if we let's say if I take uh, mm, I take a function like this uh, a naught plus a1x plus a2 x so a2 x square plus a3 x cube. So if I differentiate it once, I'll get something like a1 plus 2a2x plus 3a3 x square. If I differentiate this twice, I will get uh, 2a2 plus 6a3x. Okay. So now you can see that this function is differentiable twice. Obviously, there will be a value. If I substitute x is equals to something, uh, uh, d square of v by dx square will have some value. Okay. And this is also like the the differentiation which we are getting is also continuous. This is not a constant, right? So it is varying with respect to x. So that is also a thing. So let's take something some function vi which has four constants. So because we had a naught, a1, a2, and a3, right? So now we can use the Lagrange interpolation formula which we were using that we can exploit here, which will be n1 v1 or let's say ni vi or let's say n n1 vi plus n2 theta I, because we have two conditions which we have to like take here, because at in beam at each point there will be two primary variables, which is the transverse deflection of the beam and also the slope of the beam, which is slope is nothing but dv by dx. Okay, so that's why uh, I will take slope of the beam will be equal to theta is equals to dv by dx. So this is the consideration we will take in the uh, linear Euler Bernoulli beam. So this is like theta is equals to dv by dx. So that is something which we will take. So it can vary, like it will be different if you go to Timoshenko beam theory. This theta will not be equal to dv by dx, but in Euler Bernoulli beam theory, this will be equal. So I am replacing dv by dx with theta I. Okay, n3 into Vj plus n4 into theta j. Okay. So if you have some element like this, if you have a beam element like this, uh, and there are two nodes I and j, at each point, there will be two primary variables vi and also theta I. Okay, and there like similarly here it will be vj and theta j. Something. There are two primary variables. So for two nodes, like if I want to fit a curve uh, with these four conditions, if I want to fit a curve, uh, if you know the slope and the deflection at two nodes of the beam, like if you want to fit a curve with four conditions, you will obviously get a cubic polynomial. So you can get a cubic polynomial. Like we can, so that's why we can use cubic Hermitian interpolation. So we have learned during the start of this course, we have gone through various interpolation techniques. So here we can use the Hermitian polynomials. Cubic Hermitian interpolation can be used. So, and I also want the slope of the beam, right? So this is my displacement approximation. The slope approximation of the beam can be given as dEn1 by dx. Remember that Vi and theta I are the nodal displacements which are constants. We have to determine them. They are some constants. And this will be equal to x and theta. So now what I'll do is I will take this v cap and dv by dx, whatever which we have, and I'll substitute. Let's say I will take this entire thing. I will take this entire thing. I will take this entire thing, and I'll call it as equation one big equation itself. So I'll call this as equation one. Or and then we will substitute this. So if you substitute in this, you will get integral 0 to L d square. And also first I will take I will take a W, whatever the W which is there. I will assume this as the first basis function. So I will assume W is equals to N1. Okay. So then for the first equation we will assume this. Then we will assume W is equals to N2, and then we will assume W is equals to N3, and then we will assume W is equals to N4, and we will get four equations. So first we will take W is equals to N1. So I will have, after substituting in this, I will get this, which is d square N by dx square EI into d square by dx square of V, right? So of V cap. So that will be equal to N1 V1 or Ni Vi N2 theta I plus n3 Vj plus n4 theta j dx. So this is my left hand side. Okay. And there is also right hand side. There is also right hand side. There also you have to substitute w is equals to n1 and uh, you will get something like this, which is uh, n1 into d by dx ei into d square vy dx square at x is equals to 0. So after applying the boundary conditions, we said that these two terms should vanish because shear force and bending moment are 0. So we will be remaining only with x is equals to 0 terms. Yeah. There is also this. Okay. Okay. Plus integral 0 to L n1 q dx minus this integral 0 to L n1 q into x by L dx. So similarly, you can do, similarly, we can take W is equals to N2, W is equals to N3, and W is equals to N4, and we can get. So there will be some slight changes. Here we are getting this term. If you take W is equals to N2, you will get the another, you will get this term. You will get this term if you take W is equals to. So those are the slight changes. If you we have like if you take W is equals to N3, then these two terms both will be 0 and you will be left with this only. Okay. So we will see how that will be done. So I'm not doing it. I'm just writing it here. Okay. And let's, yeah. So we will get four equations, four integral equations we will get. So for W is equals to N1, W is equals to N2, and W is equals to N4, we'll get four equations. So all those four equations, if I take the LHS only, so now I can define, I can write them as linear equations, linear system of equations, and which will look like d square 1 by dx square ei into d square n1 by dx square dx. And similarly, this the second term will be d square n1 by dx square ei into d square n2 by dx square dx. And the third term will be, this will be n1, and here you will get the n3 term. And similarly, you will get like this. And in the second equation, we will get n2. So this will be the constant thing. And you this the change here you will get n1. Here the same thing. N2 will be there. A into d square n2 by a square. So similarly, we can do it for uh, with respect to n4 and n4. So like this, you will get a 4 by 4 matrix into vi theta I Vi theta I and Vj into theta j is equals to is equal to some boundary condition terms which we had written, right? So those will also come. Something will come. Okay. So we know that this the left end of the beam. Let's say if I am taking only this whole beam, if I am taking only a single element, a single element is taken for the whole beam. Okay, single element. This is the left node and this is the right node of the element. I can take more elements also, but it will be physically impossible to solve that in pen and paper. Like you have to write a code or do some computer programming to do that. But for simplicity, we are taking only one element here. In the assignment problem which was given, there also you have to use only one element. Okay? So at this for this at this end, Vi and theta I are zero here. Okay. So if Vi and theta I are zero, if I multiply anything, if I multiply this theta I, if I substitute this Vi and theta I as zero here, and if I multiply with this matrix, what you will get is the first two rows and the first two columns of this matrix will get eliminated, and finally we will get this matrix. Okay, simple. This is simple matrix multiplication. So we will be only get having n3 and n4 terms, which we will get like this. So this will be n3 by dx. And again, there will be n3 by dx square Vi into d square n4 by dx square dx. Integral d square n4 by dx square Vi into d square n3 by dx square dx. And this will be equals to d square n4 by dx square Vi into d square n4 by dx square dx into I will have Vj theta j, because we know that Vi and theta I are zero. So those are our essential boundary conditions. We have enforced the essential boundary conditions. Okay. Now I will have this term, which will be integral 0 to L n4 into q into dx minus integral 0 to L n3 into q into x by L into dx. This is n3, and similarly here also it is n4. X by L. Okay. So now Hermite interpolation polynomials are something which we will use here, because this is a like two ends of the elements have each end of the element, each node has two conditions. So we have total four conditions, and if you know the slope and slope of the function and also the value of the function at each point, and like if you want to fit a curve between those 2 points, you can use a cubic polynomial. So here that can be done using the Hermite interpolating polynomial. So we have already like seen this in the class. You can go and derive. So this is 1 minus 3x square by L square plus 2x cube by L cube. Similarly, we have n2 is equals to x minus 2x square by L plus x cube by L square. n3 is equals to 3x square by L square minus 2x cube by L square. We have seen the derivation of this. Okay. In the class, you can go to the class notes and refer it. If you have forgot, no need to remember this, but just have to know how we are getting this. So now if I substitute this N1, N2, N3, and N4 in this algebraic system and integrate it after performing the integration, substituting N1, N2, N3, and N4, and performing integration performing integration, I will get I will get this matrix which will be equal to EI into 4 by 9 minus 2 by 3 minus 2 by 3 4 by 3 into Vj theta j is equals to Q into 0.45 minus 0.30. Okay. So here in this and in this, I am substituting the values of n1, n2, n3, n4, and I am doing the integration from 0 to L. Okay. Over the whole length of the beam. And finally, we will get this algebraic system. So, and if I solve this algebraic system, because we have already given the in the problem the values of EI and Q, and if I take the inverse and send it here, I will get the values of Vj and theta j. That is nothing but the slope and the deflection of the cantilever beam at the free end. So the slope and the deflection, the solution can be given as solution gives Vj theta j is equals to this value, which is 0.0005625 and 0.0002344. I'm taking SI units. So this will be in meters. So if you take in mm, that will be equal to 0.5625 and 0.2344 mm. So this is the final solution which we will get. So you can see the beauty of this finite element method or this approximation method. So we had to integrate this this is our governing differential equation. If I had to solve it and get the deflection of the beam, I had to integrate it 4 times. And after getting the integration, uh, some integration I'll get, and after getting that, I have to use the boundary conditions to get the integration constants. That will be my exact solution. Okay, but if my domain is like very irregular, and if there are like a lot of irregularities in loading and a lot of things which can occur, and if I want computer to solve this problem, uh, computers are like they do everything numerically, so they don't know analytical integrations and all this stuff. So I'm making this into a I am making this into a algebraic uh, equation solving problem. So entire problem of solving the differential equation has been converted into a algebraic uh, solution. So algebraic solving algebraic equations. Yeah. So uh, and like computers are very efficient in solving algebraic equations. So if you have like a structure with 1,000 elements, because I had only a structure with I had a structure with only one element. I got this simple for 2 by 2 matrix at the end. But if I had like let's say 1,000 elements, then it will be blown up to like something. Uh, uh, I think like 1,000 elements. Then there will be 1,001, like 2,000. by 2000 uh, matrix you will get. So that can be solved easily in a computer. So going forward, we will also see like this integration which we are doing here. This can also be done in a very simple form. Like we have seen the Gauss quadrature method, and we can do the integration using that. Uh, this also can be done in a very simple way. So the simplicity can be made here also. So we will see. Like I think next week we will see how we can do. There is something called isoparametric elements. So we will see that. So this is how we will solve this uh, beam using the finite element method. So this is the system. Like we had a cantilever beam. We had a cantilever beam with a uniformly varying load, and we had to solve this to determine the deflections at the free end. Of course, this is a very simple beam. Like you can say, like I can directly integrate and get the exact solution. But if you have like very complex structure, if the beam is having, let's say, instead of uniform variation of the area of cross section, if the beam has some other area of cross section, then it will be difficult for you to integrate. And and if the loading is also like very irregular, it will be very much more complex. So then we can use finite element method. We can first we are determining the equation of the beam, equation of motion or the governing equation of the beam, and we are also determining the boundary conditions based on the structure which we have, and then we are using weighted residual method to get the weak form from the strong form. And after getting the weak form, we are assuming a solution which satisfies the differentiability condition. And then after that, we are assuming the weighting function as the interpolating polynomial n1, n2, n3, n4. And each time I assume w is equals to n1, I'll get one equation, and I'll have four equations at the end. And those four equations, I can write them as a matrix form. And after writing them as a matrix form, I'll substitute what are the values of n1, n2, n3. And after substituting the values of n1, n2, n3, I can integrate them. So I can integrate these values uh, to get this final result, which is vi into something. And if I solve this, I'll get the deflections and also the slope at the free end of the beam. So this is how we will solve uh, a beam equation. Like this will become complex if you take like because we had only one equation, there was no assembly step involved. So if you had, let's say, two elements like this, if the beam was divided into two elements like this, uh, we had to take uh, we had to take two uh, what you can say, element one, and let's say this is V1, V2, V2. We will get two system of equations for each element, and we will combine them because at the at this point, whatever this uh, beam is undergoing at this point on this element, the same deflections and also the same rotation the beam will undergo in the next element also. That is the compatibility which we will have to take care of. So then we will do the assembly, and after doing the assembly, we will solve this equations, algebraic system of equation, and we will get the solution for our displacements and also the slopes of the beam. Okay. So this was something that I think you know now how to get the equation of motion. You know how to get the equation, uh, how to do the weak form, and how to get the finite element formulation and how to solve it. So I think the assignment problem also had the same kind of problem, but different boundary conditions. So you can take care of that. Like it's very simple. Like boundary conditions and the load is changing. Everything else that is a beam and this is also a beam. Like there's no much difference. Uh, I think this was this. Yeah, there were a few things which were asked. Uh, you can get them. So they are asking transverse deflection of the beam at the midpoint. So if this is my beam, like whatever the solution which I got here, so I know that V cap is equals to N1 Vi plus N2 theta I plus N3 into Vj and N4 into theta j. So here Vi and theta I automatically become zero because this is a mm, cantilever beam, and at the left end both the displacement and also the slope will be zero, and I'll be left with N3 Vj and N4 Vj, N4 theta j. And this Vj and theta j we have determined here, right? So we have determined, we have solved, and we got this constants. So now you can take this N3. N3 is the Hermite polynomial, which you know. And if you substitute here and x is like if you want displacement, if you want the deflection at x is equals to L by 2, which is the midpoint of the beam, here you can substitute whatever the N3 term, which N3 and N4 terms which you are getting. There you substitute x is equals to L by 2 and you'll get the displacement at the midpoint of the beam. That is the thing. And potential energy is also something which can get easily. It's not about, yeah, not a very good start. And there is also a question in which they have asked this K44. K44. K44 is nothing but this term. This is the term. Is the term K44. Like this integration, you have to tell, but you should not do it directly. But you have to use the Gauss quadrature method. So for 2 points, you will like I hope you remember that. So in Gauss quadrature method, if you have let's say a to b f of x dx, then you convert it into sigma d sigma, and we can do this as w1 f epsilon eta 1 plus f w2 f2. So here W2 and W2, like if you take 2 point integration, there is Gauss quadrature table which is given. I think Week-2 notes, if you refer, you will get it. And you substitute that, you will get this and this. So maximum and minimum, you have to substitute like whatever in these two terms, whatever the maximum you will get, substitute maximum, and whatever the minimum you get, substitute the minimum. So that was what we discussed. Uh, that is the assignment. You have any questions regarding this beam theory and finite element?
One question I'm having.
Yes, please.
This whatever you explained, no, the deflection at midpoint.
Yeah.
That is supposed to be solved by assuming one element, right? Or we can take two also.
No, you can take two also, but you cannot like solve it with hand. It will become very difficult. You will get a 6 by 6 matrix.
Yeah,
you have to write a code. So here, like you have to take only one element. As I have said, like after taking one element, you will get Vj and theta j, right?
Okay.
So Vj and theta j, you know, and N3 and N4 are functions of x, right? So you substitute x is equals to L by 2, you will get the answer.
Okay, thank you.
Yeah. Any other questions? Mhm. Okay. Okay. So we'll stop it here. So this week we have also like slightly covered finite element for 3D and 2D. Like 3D, like it was started. So, but we will go deep. Like there was no question asked in the assignment. So, and also it is continued in the next week. So we'll continue our discussion starting from there for 3D uh, finite element and 2D finite element. We will look how we can use the governing equations and go about it in our next discussion. So, and yeah, I think by sixth week we'll complete sixth. Yeah, by sixth week or seventh week we'll complete finite element, and then we will go. Uh, we'll also add the dynamics. Obviously, like finite element is there, we will also add the dynamics. How, like if the load is varying with respect to time, how you can get the governing equation and also solve that. So, in my opinion, whenever you do finite element, like whenever you are like doing this course or like similar kind of course, it will always be good to do coding. Like you can, uh, let's say you have MATLAB, like I don't know what you prefer. Like you can use MATLAB and also you can use Python. So if you don't have access to MATLAB, MATLAB is a proprietary software. So like you have, your institute should have taken the subscription. But let's say if you don't have, like you can use Python, which is free of cost. Like I use like whatever, like I also write finite element codes. Whatever I do finite element, whatever the codes which I write, I use Python because like it is open source and there is a huge community and like there are very uh, lot of advantages are there. Like you can use Python, like it is free and efficient also. Like it's not uh, very different compared to MATLAB. Like at least for finite element, you can do it. Uh, there is nothing which you cannot solve in finite element with MATLAB and something like everything can be done. Like whatever it is there, like you can use. There are a lot of tools available to do that. So in this course, I think we are not going uh, in that direction. But uh, like if you are interested, uh, like to look at some code and how to do coding, please let me know. I will like in maybe in some, one session I'll uh, explain you how you can code uh, and how you can define the algorithm that, like let's say if you have 1,000 elements in the beam and like you have a very big matrix system to solve, that can be solved very easily. So we'll look at that if you are interested. Otherwise, like we will be limiting our discussion to this pen and paper discussion. That depends on you. Like if you are interested, we will one day we will look at that. Uh, Today we will stop it here. If you have any questions, you can ask. Otherwise, uh, we can end this meeting here. Thank you both for joining. I hope.
Thank you, sir.
Yeah, thanks, Anish.
Thank you.
Thank you, Sushila. Have a good night.